Hi, I'm Mike. I'm going to be talking about PACE, parallel A* for slow expansions. This is joint work with my advisor, Max Likhachev, and Sven Koenig. The general motivation of this work is pretty clear. Most of the improvements in CPU speeds recently have come in the form of additional parallelization. So in the planning community, if we want to be able to take advantage of these hardware improvements, we need to make algorithms more parallelizable. There's been quite a bit of previous work on parallelizing A*. I'm going to highlight the first one, parallel A* from the 1980s. This one does kind of the most obvious thing you would imagine. Threads just take turns pulling the best state out of the open list and expanding in parallel. This one is the most similar to what we're doing. The primary difference is that this approach allows states to be re-expanded, possibly many times, and our approach ensures that every state is expanded at most once. Most of the remaining approaches here try to distribute states across several different open lists instead of using one. So PRA* and HDA* do things with a hash function that maps states to processors, and PSDD and PBNF use a state abstraction function to map entire groups of states to their own open list, which processors can then claim and expand with very little overhead. We have a comparison against both PBNF and the parallel A*. I'll talk about those later. The primary difference between our work and all of these is that all of these methods allow states to be re-expanded, potentially many times, and what I'm going to be presenting only allows states to be expanded at most once. Our primary motivation in this work is to address the robot motion planning problem. This is the community that I come from. And the robot motion planning problem has some interesting properties that make it different from a lot of other search problems. The main one here that we're going to be exploiting is the fact that in robot motion planning, expansions are incredibly slow compared to other domains. When you expand a state and you want to evaluate the edges, come up with the cost of those edges or whether they're valid or not, there's a lot of things that need to be done in order to validate that motion. For instance, you might need to forward integrate dynamics, run forward or inverse kinematics if you're using a manipulator. And the big one here is collision checking. Collision checking often takes 80 to 90% of the time by the planner. So we're going to be taking advantage of the fact that expansions are slow here in our method. Okay, so our approach works by parallelizing state expansions out of a single open list. When you're expanding two states in parallel, it's not clear which one is going to finish its expansion first. So in order to expand two states in parallel, you have to be comfortable allowing either expansion to finish first. Basically, you have to be comfortable with allowing out-of-order expansions. So here's an example here with an open list and two states, S and S prime. And let's say that S is at the front of the open list. So in A*, the state S should be expanded first. But in order to do parallel expansions, what we're interested in is seeing if it's possible to let S prime expand first instead. So in order to do this, I'm going to introduce a concept called independence. And in independence, what we're saying is that two states are independent, let's say S. If S or any of its successors cannot reduce the G value of S prime, then we're going to say that S prime is independent of S. And this means that it's possible to expand S prime before S. So here's an example down here at the bottom that's going to show the opposite of this. So we have two states, S and S prime. And let's say that there is some optimal path connecting them with a cost of 3. So in this case, expanding S and its successors could reduce the G value of S prime from 7 to 5. So this is a case where S prime is not independent of S, and you wouldn't be able to expand these in parallel. But in many cases, there is a lot of independence in A* search. And so the key idea of our approach here is that we're only going to expand states that we're sure are independent of all other remaining states you could choose for expansion. And this is going to ensure that every state only needs to be expanded once. Okay, so how do we actually determine independence? So formally, how we're going to define independence is according to this rule here. So state S prime is independent of another state S basically if its G value cannot be reduced. So we have the G value of S prime. If it's already less than or equal to the cost of getting to S plus the cost of getting from S to S prime, if the G value is already less than or equal to that, then we know that S cannot affect S prime at all. One important assumption of this rule is that we're assuming that G of S is not going to change. So G of S is not going to improve anymore. And this is true as long as we know that G of S itself was safe for expansion in the first place. So here's an example down here. We have a state S prime, and you can see that C star in this case is 9. So G of S would be able to arrive, S would be able to arrive at S prime for a cost of 12. So this means that S prime is independent, and we'd be able to expand these in parallel. But C star is hard to know in advance, obviously. So we're going to instead assume that we have an admissible heuristic, pairwise one, for any pair of states S and S prime that's always less than or equal to C star. For the proofs, we actually need H to be forward-backward consistent. For the intuition, you just need to know that it's admissible. So we're going to replace that 9 there, which is the actual C star, with a heuristic with a cost of 5. And now we can change our rule to use this pairwise heuristic instead of C star. So that's our new independence rule. And we can see that in this case, using the heuristic, that at best, S prime's G value, or S prime can be reached from S with a cost of 8 by adding the 3 and the 5. So we know in this case that S prime is safe to expand in parallel. In addition to the independence rule, we also introduce in the paper the concept of epsilon independence. And here we're going to inflate the heuristic on the right-hand side of the inequality by parameter epsilon p greater than or equal to 1. And this is going to make the right-hand side larger in general, and it's going to make it easier to satisfy this inequality, and therefore you can have increased parallelization. And one of the cool things about this is we have an interesting guarantee. So again, only allowing states to be expanded at most once. We can guarantee that the solution we find is no larger than epsilon p times the cost of an optimal solution. So for instance, if you set epsilon p to 1, which is what happens in the original independence rule, you're guaranteed to get the optimal solution in the parallel situation, even though every state is only expanded at most once. Okay, so one caveat here that I glazed over is I said we need to check independence against all other possible states we could check for expansion. So this means checking against all the states in the open list, which sounds like a huge amount of overhead. But a pretty reasonable question would be, A star doesn't need to do any of these kind of checks. It takes the first state in the open list and it expands it, and it doesn't do any checks against the rest of the open list. So this must mean that the F value that A star uses, G plus H, must somehow encode the independence checks against the rest of the open list. So let's see if we can find the connection here. So let's say that S has the minimum F value, it's at the front of the open list. We're going to ask the question, just by looking at the F value, can we tell that it's automatically independent of any other state S prime? So this is pretty easy to show, in fact. We just say, F of S is less than or equal to F of S prime. We expand these out to be G plus H. We move the one heuristic to the other side, and then by applying the triangle inequality, it turns out you can turn these two heuristics into the one pairwise heuristic. And this should look very familiar because this is, in fact, our independence rule. So it turns out that if your F value is less than or equal to any other state, you're automatically independent of it. So basically, the ordering that the open list already provides eliminates the vast majority of the independence checks that you need to run. And this is a pretty interesting generalization of the A star expansion rule. You actually have a pretty wide variety of states you can choose for expansion and still guarantee optimality. So I'm going to go through an example real quick to see how we use the independence rule in practice in an A star search. So let's say we have 3 threads, and we have an open list here on the right. And then we have a new list called being expanded, which I'm going to abbreviate as BE in a second. And that just shows what state every thread is expanding. So first, thread 1 is going to try and grab a state from the open list. So it's going to try and grab state A. A is automatically independent of everything because it's at the front of the open list. So it just gets the state. And we can see that thread 1 is now currently expanding state A. Thread 2 tries to take state B. It doesn't need to run an independence check against anything else in the open list because of the F value, but it needs to run an independence check against A because A in this case, let's say, has a smaller F value than B. Let's say that passes though. So this means that thread B can safely expand a state in parallel, thread 2 in parallel with thread 1. Then we have thread 3 that tries to take a state C. It doesn't need to check against anything else in the open list, but it needs to check against A and B. Let's say the independence check against A fails. In this case, thread 3 would now try to take state D for expansion instead. It doesn't need to check against anything after it, but it needs to check against C because it comes before it in the open list, as well as states A and B. And then let's say this passes. So now we have 3 threads expanding states in parallel. And if thread 1 were to finish its expansion, then thread 1 would go back and grab the next state C, run only an independence check against state B, and so on and so forth. So this is how the PACE algorithm works. In addition to running A star, PACE has been extended to the weighted A star case, which is commonly used for solving harder problems. In weighted A star, you have the priority function f equals g plus wh. And we have a nice guarantee here. As long as w, the weighting for weighted A star, is less than or equal to epsilon p, our parallel weight, still only allowing every state to be expanded at most once, we can guarantee the solution is no larger than just epsilon p times an observable solution. So you can, once you have epsilon p raised up, you can always bring your weight for weighted A star all the way up to epsilon p without affecting the suboptimality bound. Okay, so like I said, we're interested in robot motion planning problems. So here we have a domain that we ran tests on, which is a 3D planning domain for XY position of the robot, as well as the heading that the robot is facing. And we're doing 3D full body collision checking, which is incredibly expensive, but it's needed in order for the robot to fit through really tight spaces. So here, when the robot needs to fit between the chairs and the table here, you'll see up in this picture, you'll see that the base of the robot actually needs to tuck under the table. The arms of the robot holding the laundry basket need to go over the table. So you need to do this full 3D collision checking in order to even find a plan between these two places. Okay, so this first plot is on a bunch of trials that we ran with the robot. I'm going to direct your attention to the first blue line. So each of these all the points in all the blue lines are speedups over single-threaded weighted A star for a weight of 1.5. This first blue line also has a weight of 1.5, and we vary the number of threads on the x-axis. So you can see that if we go all the way out to the right, this is saying that for 8 threads, we get about a 6 times speedup over weighted A star with a single thread. And you get a similar trend where speed improves as the number of threads increases. In order to get a more in-depth analysis of our method, how it's affected by the amount of expansion time, remember I said expansions need to be slow. So in order to analyze what happens as you make them slower or faster, and tuning other parameters, we ran a whole bunch of tests on Nathan's set of benchmarks for 2D grid pathfinding. So in this first slot, this is to see what happens as we change the expansion time for our method. I want to first direct your attention to the dashed blue line. In this case, we're looking at speedups over single-threaded A star. All the stuff you see in this plot is for optimal search. And what we see here is that for 16 threads on this dashed blue line, we get about a 15 times speedup. So the dashed blue line has a sufficiently large expansion time for our method, and you get pretty much close to a linear speedup. However, you can see that with the subsequent curves, where expansions get quicker and quicker, you can see that the performance drops off as the expansions get faster. For instance, even in this last curve, you can see that it actually would be better to have 16 threads than 32 threads in this case. Okay, this next plot shows a speedup over parallel A star from the 80s, the one that allows re-expansions. And now on this axis, we're looking at the speedup over that method. For each data point, we're using the exact same number of threads, and we're using the exact same suboptimality bound, so the same weighting. So the only thing that's changing between our two methods that affects the speedup is whether we're doing re-expansions or not. And you can see here that for a weight of 1.5, the speedup of our method, we get about 2.3 times faster speedup over parallel A star from the 80s. And this ends up being true for all 4 of the lines. The lines indicate a different number of threads. So you can see that actually the number of threads does not make an impact here. Recall that we're running both methods with the same number of threads. So the speedup entirely comes from eliminating re-expansions. And as the weight gets larger, the speedup gets more. This kind of makes sense because as you run a weighted A-star search with a higher weight, you tend to get more re-expansions. Whereas, for instance, for the optimal case, there's very little speedup. We also compared against a modern method, very recent, called PBNF. I want to say a disclaimer very early on. PBNF has a couple parameters. I tuned them specifically for the 8-thread case. So that's the case with the plot line with squares in it. So this is the one that's most representative of the lines. So in this case, again, we're comparing over the same number of threads with the exact same suboptimality bound, the exact same weight. And we're looking up speedup of our method over the PBNF method. So here's an example here. For a weight of 1.5, we get about a 2 times speedup, which is not quite as good that we did against the previous method. And for a situation with a weight of 2, we get about a 2.5 times speedup. Again, not as good as against the method from the 80s, where we had over a 3 times speedup. The other thing that I want to point out on this slide, which is very important, this, again, is for sufficiently slow expansions. If we had very fast expansions, as you might see in other kinds of search problems, we wouldn't get any kind of speedup over PBNF. Okay, this is my conclusion slide. And actually, I have one other slide that I might go to if I have time. In general, though, I'm going to say I presented a PACE, which is a parallel version of Dijkstra's algorithm, A-star and weighted A-star, specifically for scenarios when expansions are slow. And we're able to do this in a way that only allows states to be expanded at most once, while we can guarantee optimality, and in the case of weighted A-star, bounded suboptimality. We get a near linear speedup in the number of processors for sufficiently slow expansions. And we've introduced we've introduced independence and the epsilon independence rules, which are an interesting generalization of the A-star expansion rule, and in the future might provide ways to have new search algorithms that can choose a little bit better over what state to expand next in the search. We think this is an interesting future direction. At that point, I'll conclude and take any questions.
The way you presented this, it sounded like the speedup was entirely due to avoiding re-expansions. So did you actually directly measure the number of re-expansions that the other algorithms were doing, or and maybe there's some other factor that's that's causing the speedup as well?
Yeah, that's a great question. We did measure both expansions and planning time. I only presented the planning time here because it's more useful in practice. But the speedup in terms of expansions is almost identical to the speedup that comes from time. One other plot that was not included here for the PBNF and the parallel A-star for time reasons is path quality. And you can come to my poster if you'd like to see it. But in general, we have about PBNF and the parallel A-star from the 80s do about 10% better in terms of path quality than our method.
It's a somewhat tangential question, but what have you tried this A-star when you have, let's say, arm planning for the motion of the arm, and you have possibly an 18-dimensional space? Then what happens then? And are you able to do any kind of parallelization in the different dimensions?
We have not run the experiment on manipulation. Our lab does do a lot of manipulation type experiments, so it's likely something we'll try in the future. There's nothing inherent about this method that would make it not apply to this scenario. As I said, the real assumption we're making is that the expansions are slow, which is equally true for manipulation problems. There's expensive collision checking and running forward in inverse kinematics. So this assumption will definitely hold. The other one is that you have a quick to evaluate pairwise heuristic function, which could very easily be implemented in like Euclidean distance in configuration space. So it should work equally well for manipulation type problems.
So something that I think is an assumption here is that the triangle inequality holds.
Yes, that's definitely true. So
no dead ends and that kind of thing?
right, yes. So as I said, for the intuition, you just need to know that the pairwise heuristic is admissible. But for the proofs on the suboptimality bound that we showed, you actually need forward-backward consistency. So consistency for any pair of 3 states.